Now we're going to bump up our systems of linear equations to 3 variables. So 3 equations, 3 unknowns. So when we think about this, we're still trying to find, is there an x, y, and now z coordinate that satisfies all 3 equations simultaneously? Because they're linear though, they're going to have the same possible outcomes. So we could still have one solution, we could have no solutions, or we can have an infinite number. When we talk about a linear equation in 3 variables, it now becomes a 3D shape. So it's going to be a plane in 3 dimensions. And so a plane is just a flat surface that extends forever. So here's just some visuals as to what can happen here. So in the case that we have one solution, there is one point where those 3 planes intersect. For an infinite number, there's an infinite amount of points where these planes meet. And then no solution could be the case where all the planes are parallel. 2 of the planes are parallel, so there's not a point that satisfies all of them. Or just other funky stuff kind of happens, and then there's no way that these 3 are going to overlap in a single point. When we talk about solving these systems, you are going to have to use elimination. So with 2x2 systems, 2 equations and 2 unknowns, there's no issues at all. You can use elimination or you can use substitution. But here I have to use elimination. So your goal is you want to take this system and you want to reduce it to 2 equations and 2 unknowns. And then we can use our methods that we already know to solve those. So when I look at this equation, this x being a 1 out front is really nice because I can multiply this by numbers to cancel out the 2x in the second equation and the negative 3x in the third. So my x is a really nice number to eliminate from my system. You could also use the second equation because you have a single y, and I could get rid of these y values in each equation. But since that x is in that first spot, we're going to work with that. So I want to eliminate x from my other 2 equations. So what I want to do first is I want to eliminate it with the second. So I need a negative 2 out front to make these 2 cancel each other. So to get rid of that x, we're going to do negative 2 times the first equation. And we're going to add that to the second equation to be able to eliminate x. Okay. So if I take negative 2 multiplied by this equation, that's going to give me negative 2x plus 4y minus 6z equals negative 14. Right? And then I've done nothing to the second equation, so I just go ahead and I copy that down. Now I want to add these 2 equations together because it gets rid of my x. So that leaves us with 5y minus 5z equals negative 10. And then to make life easier, all of these are divisible by 5, so might as well go ahead and get rid of that. And I end up with y minus z must equal negative 2. So I've got one equation now involving 2 unknowns. So I need a second one now. So I want to do the same thing, but now I want to use 2 different equations. So if I look at the x in the first and the third equation, to get rid of it, I need a 3 out front. So I also need to do 3 times the first equation, add that to the third equation to in turn eliminate my x again. Okay. So when I do 3 times this first equation, that gives us 3x minus 6y plus 9z equals 21. And then I just go ahead and I copy what I have for the third equation down. And now when we add these 2 together, the x's cancel again. And what I'm left with is negative 4y plus 7z equals 11. And now, unfortunately here, I don't have any way to get rid of any of those constants. There's nothing in common to the two. So in eliminating the x, we now have resulted in two equations and two unknowns. So what I want to do is I want to solve this system. So we need to solve y minus z equals negative 2 and negative 4y plus 7z equals 11. All right. So let's go ahead, let's do that on the next screen because I definitely don't have room here. At this point, you can use elimination or substitution, purely a preference. I'll go ahead, since we just did some elimination, let's do substitution. If you want to look in the notes, I did elimination there though. But from this first equation, I can go ahead and I can add z to the other side to get that my y is equal to z minus 2. And then plugging that for our y into the second equation, this tells us negative 4 times z minus 2 plus 7z needs to equal 11. So we've boiled this down to an equation just involving z. We go ahead and solve it by distributing this. That gives us negative 4z plus 8 plus 7z is 11. And then combining my z's, this is 3z plus 8 equals 11. So we go ahead and isolate our z by subtracting 8. This gives us 3z is equal to 11, or 3z equals 3. Can't subtract there. And then we go ahead and we divide by 3. And that gives us our z value is equal to 1. So because I got a set value for z, this means there is a single solution. Now I need to figure out what are the other variables. But since we have z, we know our y is z minus 2. And so we just plug in that z has to equal 1. So our y is equal to 1 minus 2. Our y coordinate then equals negative 1. Okay. The only thing missing now is x, so that means I have to go back to my starting equations. You can pick any one of these three, plug in y and z, find your x. I'm just going to use this first equation. So copying that down, our first equation tells us that x minus 2y plus 3z needs to equal 7. Okay. We just figured out that our y is negative 1 and our z is positive 1. So we have now just a single value of x. Distributing that out, that's x plus 2 plus 3 equals 7. And then moving up here, this is x plus 5 is equal to 7. And so finally, subtracting 5 gives us that our x must equal 2. Okay. So our solution, you could write it out as x equals 2, y equals negative 1, z equals 1. Or you can write it as the coordinate pair 2, negative 1, 1. Either one works. So unlike the last section, you can sometimes easily tell when you have no solutions or infinite number of solutions. You can't quite do the same with 3 equations and 3 unknowns until you get it to the 2 equations with 2 unknowns. So let's do one more example where we're going to solve this system. So again, I want to eliminate a variable. You have a lot to choose from because all of the variables at least have just a single value. I'm going to go ahead and I'm going to eliminate my x value again using this x here because it's very easy to manipulate to get it to be the same value in front of the first equation and the second equation. So the first thing I want to do is I want to take this equation and I want to multiply it by 3. So this way these two are opposite in signs. So when I do that, my first equation is still the same. And when I multiply the second equation by 3, it gives me 3x plus 6y minus 9z equals 12. Okay. So when we add these together, our x's cancel, and this gives us 5y minus 10z equals 14. So we get one equation involving our two unknowns. Okay. Now I want to do the same thing, eliminating another variable, or eliminating x from the third equation. So I'm going to take this and multiply it by -2. So this way these are opposite in signs. So when we do that, the second equation becomes -2x minus 4y plus 6z equals -8. And then our third equation is 2x minus y plus 4z equals 6. So when we go and add these two together, the x's cancel, and that leaves us with minus 5y plus 10z equals -2. So if you notice, the left-hand side is just opposite in signs, but that's not the same for the right. So when I go to solve this system, there's going to be no solution. But let's actually do that. We have 5y minus 10z needs to equal 14, and -5y plus 10z equals -2. This one, thankfully, is completely prepped for elimination because we can just add these two together. It makes our y's cancel, but it also makes our z's cancel. So we're left with nothing on the left and 12 on the right. So because we ended up with no solution to the two equations and two unknowns, just overall, there is no solution to this system of equations.